and then I will post it, and you guys can watch it later. But real quick, I'm just gonna show you guys this. So this is Staples, as you can see right here. Um, Inflation 23.69. I don't want y'all to pay that though. Staples will price match whatever price you can find online, right? So if you go to like Walmart, for example, or like what's that other one? Amazon, for example, and you see it there for like 19.99, right? Staples will price match that. So you just go to the Staples and you say, hey, but online it's for this price, and then they'll charge you that price for it. All right. This calculator does everything that you need in this class and more. All right. I'd love to show you guys how to use this on your final. All right. And they also do like 1 hour pickup. So if you go to like staples.com, you can just click on 1 hour pickup, check availability, put in your zip code to whichever one is the closest to you, and then boom, boom, and then that's it. All right. Hello, hello. Come in. Hi. You here for calculus? You're, no, what you here for? 28.5? Oh, that's next door. We're 23.5. You're welcome. Telling you calculus would have been easier. Mhm. All right. So we're back. So my lessons are gonna kind of seem a little bit choppy. It's not gonna be like when you guys first took 23. I'm kind of just going straight to the meat and potatoes with everything a little bit. But I am gonna teach you like the meaning behind what we're doing too. Because hopefully on the test, if you forget what to do, you can at least remember the lesson, and maybe the lesson can help you get through the question a little bit. All right. So this is our first topic. All right. So we're gonna do measures of central tendency, mode, median, and mean. All right. Now on your test, we're not gonna be asked to do the mode, but we will talk about it. Because I know in your classes you might have learned a mode, and even though that wasn't asked of you on the test, maybe you might have given that by accident, kind of thing. So I want y'all to know the difference between all of them and when to use them. Right. But when to use them is whenever they ask you, that kind of thing, right? All right. I want to start off with like a little story, a little bit. Okay. Oh, by the way, is this clear for everybody? Everybody can see, no problem. It's good. Everybody can see. All right. Let me just get rid of this little okay thing right here. All right. All right. I think we're good. I think we're good. Okay. So I just want to start with a little story. So the average price of an ounce of gold is $1,350. The Zippy car averages 39 miles per gallon on the highway. A survey showed the average shoe size for women is size 9, right? So in each of the preceding statements, one number is used to describe the entire sample or population. So such a number is called an average, all right? So there are many ways to compute averages, but we will study only three of the major ones. The easiest average to compute is the mode, all right? So again, mode will not be asked, but I want you all to know the difference. All right. So here you go. So the mode of a data set is the value that occurs the most frequently. So note, if a data set has no single value that occurs more frequently than any other, then that data set has no mode, right? So if I have a set of numbers in front of me, however many numbers there are, right? The one that repeats itself the most, that's the mode. All right. The one that repeats itself the most is the mode. All right. Any questions on that? Good. All right, help me out real quick. What's the mode? Three is a mode? Four. Four is a mode, right? It's the one that repeats the most, right? The most. All right, cool. So we get the gist of that, right? All right, so scanning the data, right? We see that four is the mode because more words have four letters than any other number. For larger data sets, it is useful to order or sort the data before scanning them for the mode, right? All right. This is a little special note, real quick. So not every data set has a mode, right? For example, if Professor Fair gives equal numbers of A's, B's, C's, D's, and F's, then there is no modal grade, right? In addition, the mode is not very stable, right? Changing just one number in a data set can change the mode dramatically. However, the mode is a useful average when we want to know the most frequently occurring data value, such as the most frequently requested shoe size. Another average that is useful is the median or the central value of an ordered distribution. So when you are given the median, you know there are an equal number of data values in the order distribution that are above it and below it. All right. So you hear the word median, you think of the word middle, median, middle, median, middle, right? So median is the middle number, right? But before you give me that middle number, you got to put all the numbers in order, right? I'm not picky. However you want to put them in order is however you want to put them in order. If you want to go from highest to smallest, that's cool. You want to go from smallest to largest, that's cool. I don't care. Put them in order. Give me the middle number. All right. That's it. In our test, they're gonna ask you for the median. All right. I know sometimes some people like to see it written out, so this is for those that like to see it written out. Here's a procedure. So how to find the median? The median is the central value of an ordered distribution. So to find it, order the data. You can either do it from smallest to largest or largest to smallest, right? I feel like smallest to largest is the easiest way. So that's why I put that on, right? Okay, two, right? For an odd number of data values in distribution, the median is the middle value, right? So if I have three numbers, right, the median is the middle number. It's in the middle. That's in the middle, right? So imagine I had one, two, three. My median is two because it's in the middle, right? For an even set of data, or even set of numbers, right? There's a formula to find a median, right? So the median is equal to the sum of the middle two digits divided by two. Okay, let's say that I had a data set. Let's say it was, I'm just keeping it simple. One, two, three, four. One, two, three, four. Just those four numbers, right? I have an even set of data. I have two middle numbers, two and three, right? So what am I going to do with the two and three? I'm going to add them together. So two plus three is five. Then I'm going to divide by two. and I'm going to get 2.5. So my median for that data set that has an even set of data, right, is 2.5. Questions on this? Make sense? All right. I just want to look at an example real quick. So what do barbecue flavored potato chips cost, right? So according to whatever, the prices per ounce in cents are of the rated chips are 19, 19, 27, 28, 18, 35, right? What's the median? That's my question to you. What's the median value? I'll even take that. I know we don't have the calculator for today, but I got you. All right. But before you give me those numbers, you have to put them in order. All right. And then you get the two middle numbers, you add them together, divide by two. That's it. All right. So let's talk about a little bit. So to find the median, right, we first order the data and then note that there are an even number of entries. So the median is constructed using the two middle numbers, right? So we have 18, 19, 19, 27, 28, 35, right? So our two middle numbers are the 19 and the 27. So what we're going to do, we're going to take the 19 and the 27, we're going to add them together, then we're going to divide by two, and we get 23. That's simple, right? This is for an even set of data. If it was odd, it's just the middle number and then that's it. Questions on this? It makes sense? All right, you guys okay too? Make sense? Yes? All right. All right. Let's keep it moving. So, according to Consumer Reports, right, the brand with the lowest overall taste rating costs 35 cents per ounce. Eliminate that brand and find the median price per ounce for the remaining barbecue chips. Again, order the data. Note that there are an odd number of entries. So the median is simply the middle value. So I have 18, 19, 19, 27, 28. Middle number there, 19. That's it. All right. Questions on this? Make sense? All right. Let's keep it moving. All right. Nothing crazy today. So 1 ounce of potato chips is considered a small serving. Is it reasonable to budget about $10.45 to serve the barbecue flavored chips to 55 people? Right? So here's what it's saying, right? If I wanted an ounce of potato chips, right, it might cost me about, let's say, 19 cents, right? I want to feed 55 people, right? So do you think that $10.45 is enough to budget to feed the 55 people? That's what they're asking. All right. So what do you guys think? Yes or no? No. Remember, it's a potato chip, so an ounce is not like one. An ounce is like many, you know. Yeah. All right. So yes. All right. So since the median price of the chip is 19 cents per small serving, right? This budget for chips assumes that there is plenty of other food, right? Fun stuff, fun stuff. So let's just talk about the median a little bit more. So the median uses the position rather than the specific value of each data entry. If the extreme values of a data set change, the median usually does not change. This is why the median is often used as the average for house prices, right? If one mansion costing several $1 million sells in a community of much lower priced homes, the median selling price for homes in the community would be affected very little, if at all. All right. So basically, like if we talk about the Bronx here, y'all know we got mansions over here in Riverdale, right? But those mansions don't affect our housing prices what we got, you know? That's what that is saying. We also use it for salaries too, because y'all know y'all all gonna be making six figures one day, you know? So it's gonna help y'all with that. Let's make a special note. Whoops. Okay. So for small order data sets, we can easily scan the set to find the location of the median. However, for large order data sets of size n, it is convenient to have a formula to find the middle of the data set. All right. For your test, you're not going to have a large data set, but this is just more for like your own personal knowledge with y'all majors and stuff like that. So let me give y'all that magic formula. I feel like it's not on the formula sheet though. This formula. Yeah, this formula is not on the formula sheet, but let's talk about it real quick. I feel like it's really useful to know. All right. So for an ordered data set of size n, right? The position of the middle value is going to be equal to n plus 1 divided by 2. All right. Let's say I have hold on, is that snow? My fault. I'm sorry. I didn't mean to get distracted. All right. Let's say I have yeah. No, because I'm just looking, I'm just like, what? Yeah. Yeah. I mean, we at the highest point in the Bronx, so it makes sense. All right. Let's say I had like 55 numbers. I'm just coming up with something on top of my head, right? Now I want to know what is the middle number. Now, first off, I got to put all these numbers in order from smallest to largest, right? And then I don't want to, how can I say something? It's not easy for me to just look at 55 numbers and be like, okay, like you're the middle. Like, no, like I kind of have to go through it, right? If I use this formula, all I got to do is just count to where the middle position is, and then that's it, right? So, for example, right? 55 numbers. If I plug in 55 for n, this becomes what? 55 plus 1 is 56. And then 56 divided by 2, what's that? Like 25, 26, 27. That's like what? 28, right? All right. So if I have all the numbers in order, right? From the first number all the way to the 55th number, right? The 28th number, that's the median, right? So I don't gotta look at all the numbers to figure it out. I can just count it off like one, two, three, four. Okay, 28, boom, that's the number. Whatever that number wants to be. Does that make sense? Yeah. Okay. No?
So take the whole, um, all the data
Mhm.
plus one and divide it by two.
Right.
And
So
that's like-
so I'm not taking the actual data values. I'm taking the counts of them, like how many there are. So in like in my scenario that I just told you, right? I have 55 numbers. These numbers could be anything. They could be like 2.5, 3.8, 9.10, whatever, right? The point is that there's 55 of them, right? And I want to know what is the median of those 55 numbers, right? So I just plug in the formula, bop, 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 and I know where I can find the median at. I know it's the 28th number, right? So all I got to do is count it off. After everything is in order, just count it off. One, two, three, four. Okay, 28. Boom. And then that's that, whatever that number is, that's my median. That's all this is saying. All right. Let's elaborate a little bit more. All right. So, for example, if n was equal to 99, so I have 99 numbers, right? Then the middle value is 99 plus 1 divided by 2, which is 50, right? The 50th data value in the order data set, right? That's going to be the median. So if n equals 100, then 100 plus 1 divided by 2 is 50.5. This tells us that there's going to be two middle numbers, right? The 50th number and the 51st number, right? So whatever those two numbers are, you already know what we're going to do. We're going to add them together and then divide by 2 to find the median, right? So when it's an odd set of numbers, we're going to have a 0.5, right? When it's an even set of numbers, it's going to tell us flat out it's this position and then that's it. All right. This is just something extra for your knowledge. Your test questions are only going to have like 5 numbers, so you'll be able to look at it with your eyes and figure it out, right? After you put it in order. All right. Can't stress that enough. After you put it in order. Okay. All right. Let's keep it moving. Something else that they're going to ask you on your test, right? So an average that uses the exact values of each entry is the mean, sometimes called the arithmetic mean, right? Arithmetic mean. I can't. Oof, I'm stuttering today. So to compute the mean, right? We add all the values of all the entries and then divide by the number of entries. All right. So to find the mean, you add up all the numbers that you're given and you divide by how many numbers are there. All right. Just to kind of make it look nice. This is what I'm trying to say. All right. So the mean is equal to the sum of all the entries divided by the number of entries. Right. The sum of all the entries divided by the number of entries. All right. I want to point out on your formula sheet, chapter 3, right? At the very top, it says sample mean. That's what this is, but it's in English, right? If you look where it says x bar is equal to sum of x divided by n, this is what it means. It's the sum of all the entries divided by the number of entries or the count of the entries. All right. I just want to look at an example real quick. All right, mean. So to graduate, Linda needs at least a B in biology, right? She did not do very well on her first 3 tests. However, she did well on the last 4 tests. So here are her test scores, right? 58, 67, 60, 84, 93, 98, 100, right? And now here's what we're being asked to do. Compute the mean and determine if Linda's grade will be a B. And remember, B is between an 80 and 89 average, or a C, which is between a 70 and a 79 average, right? So we want to compute the mean. So what are we going to do? We're going to add up all of the numbers and divide by how many numbers are there, right? If you want, I'll give y'all a few minutes. Y'all could try it before we look back at it. Go ahead. You got 80? Okay, okay. All right. So she gonna get a C or a B? Which one? Good, good. Let you guys take a minute to try that. Yeah, 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 no problem. You know where it is in the building? All right, so right now we on the third floor, so you gotta go down to the first floor. It's right there. Yeah. By the way, that's just for us guys. Like you guys have a bathroom right there. Mhm. Yeah. There's a big one on the second floor. Is it two? No, there's one. Yeah, there's one big one by the staircase on the second floor. But there's another one right here. It's kind of funny though, like because you have to like read the door and it's like in small print. It says bathroom, but it's not like obvious, you know? Yeah. 1 second. All right. So in addition to teaching you guys, right, I actually tutor in the tutoring lab as well. Um, I'm gonna be there every day after class if you guys want to join me. All right. The hours are gonna be from 12 to 6. We finish class at 1 o'clock every day. So you guys can just go right there, knock out your homework. I promise you it's not gonna be that much, right? Maybe half an hour tops it'll take you to finish your homework. You know, like it's gonna be quick, right? Just go in there, knock it out, go home, enjoy the rest of your day. Right. But if you want to stay longer, I'm gonna stay till 6 o'clock every night. So you guys are welcome to, come by. All right. But what I was doing was I had to message them because they don't know that I'm gonna be late today. So it is what it is. By late, I mean I'm going after class. All right. They're under the impression I'm gonna be there at 12, but class actually ends at 1. So that's how that's going on. Anyway, let's get back to this problem real quick. It's gonna be good, right? So just to recap, the mean is equal to the sum of the scores divided by the number of scores, right? So that's going to be what? The 58 plus the 67 plus the 60 plus the 84 plus the 93 plus the 98 plus 100 divided by how many numbers that we have? We have 7 tests. So divided by 7. That's going to give us the 560 divided by 7, which when you do it in the calculator will give you 80. So since the average is 80, Linda will get the B that she needs. All right. Questions on this? So we're all good with mean?
That's a sample mean, right?
Yep, sample mean. Yep. Now I know that everybody here is gonna graduate BCC one day. You guys might want to pledge into a fraternity or something. So let's talk about the Greek letters a little bit. All right. So just to make a comment, so when we compute the mean, right, we sum the given data, right? So there is a convenient notation to indicate the sum. Let X represent any value in a data set, then the notation, the sum of X or sigma X, right, is read as the sum of all the given X values, right? This sigma X is what you have on your formula sheet right here on the sample mean, right? Sigma is this letter that's in front of the X right here. And it means sum of, right? That's also capital letter S in the Greek alphabet. Right? So sigma X means that we are to sum all of the data values. In other words, we are to sum all the entries in the distribution. The summation symbol, sigma, means sum the following, and it's capital sigma, right? That's another thing too. That not only is that S, that the way that it looks right there, that is capital S in the Greek alphabet. All right. There is a lowercase s also. All right. But that is capital S. All right. In the Greek alphabet. Fun stuff. Mhm. So the symbol for the mean of a sample distribution of X values is denoted by X bar, which is read as X bar, right? If your data comprise the entire population, we use the symbol mu or the lowercase Greek letter mu, right? To pronounce mu as to represent the mean, right? So whenever you see X bar, that's sample mean. Whenever you see the Greek letter, lowercase mu, right? That's a U looking thing, right? That is population mean, right? And when you're on your test and you forget, it's right here in chapter 3 on the formula sheet. Okay. Real quick, let me just put this up so we can see. Little procedure, how to find the mean. So compute the sum of X, that is to find the sum of all the data values. That's the first thing that we do to find the mean. After that, we divide the sum total by the number of data values. And we have two types of mean. We have the sample statistic X bar, which is X bar is equal to the sum of X divided by N. And we have the population parameter mu, which is mu is equal to the sum of X divided by capital N. Capital N means it's the entire population. Lowercase n is just the sample size that we have, right? And when you're on your test and you forget what I just said, it's right here at the top, right there. All right. Lowercase n, sample size, capital N, population size. All right. Where n is equal to your number of data values in the sample, capital N is the number of data values in the entire population. All right. Everything is right there. Just copy and paste. One second. So I kind of just want to like sum this all up a little bit. So what do averages tell us, right? So an average provides a one number summary of a data set, right? The mode tells us the single data value that occurs most frequently in the data set. The value of the mode is completely determined by the data value that occurs most frequently. If no data value occurs more frequently than all the other data values, there is no mode, period. The specific value of the less frequently occurring data, right, do not change the mode. All right. Wait, the specific values of the less frequently occurring data do not change the mode. The median, right? Median middle, right? The median tells us the middle value of a data set that has been arranged in order from smallest to largest. The median is affected by only relative, position of the data values. For instance, if a data value above the median or above the middle two values of the data set with an even number of data is changed to another value above the median itself does not change. All right. So it's basically what it's saying is that if the numbers that you have in there, if they suddenly increase or decrease, right? Like an actual entry was to change, it's not going to change what the median itself is. That's what it's trying to tell you there. All right. More for your own knowledge than anything. All right. The mean tells us the value obtained by adding all the data and dividing by the number of data values. As such, the mean can change if just one data value changes. On the other hand, if data values change but the sum of the data remains the same, the mean will not change. Okay? This is just a couple of notes for you guys for your own personal use. So we have seen three averages, right? The mode, the median, and the mean. For later work, the mean is the most important. A disadvantage of the mean, however, is that it can be affected by exceptional values, right? So what they're trying to say there, right? Let's say that like what's a good example? Let's say that we took everybody's future salary, right? How much money everybody in this room is going to make in the future, right? Some people are going to be making more money than others, right? Now, those people who are making far, far more than everybody else, that's going to throw off what the mean value is, right? It's going to make it look like this group of people here is making more money on average than what they actually are making on average, right? Another way to think about it is you know what, let's talk about the news, right? Y'all heard about what happened with the that CEO in Manhattan, right? United Healthcare and all that, right? So he has a whole bunch of employees that are making minimum wage, right? Meanwhile, he's making $15 million a year, right? So if you took all their salaries together and found an average, right? Meaning that we add them all up and divided by how many we have, right? It would look like everybody that works at that company in general is doing very, very well, right? But in actuality, it's not like that because he's over here making 15 million, but everybody else is over here only making like 30,000 a year, you know? So that's what this last comment right here is trying to say. Mhm. Another way of saying what I'm trying to say is that when you have someone who has a value that it's when you have a data set that has a value that is either too big or too small, it skews the data. That's what I'm trying to describe, the skewing of the data. All right. Again, this is for your knowledge. Not going to be asked on the final, but want you guys to understand. All right, what's going on. All right, we're gonna make a little bit of a jump forward. We're gonna talk about measures of variation. All right, measures of variation. All right, so an average is an attempt to summarize a set of data using just one number. As some of our examples have shown, an average taken by itself may not always be very meaningful. We need a statistical cross reference that measures the spread of the data, right? The range is one such measure of variation, all right? So let's talk about range a little bit. So the range, right, is the difference between the largest and smallest values of a data distribution, all right? And I don't believe this is going to be asked in your test, but formula sheet chapter 3, range is right here. You guys can see it right there. So it's the difference between the largest and the smallest value of the data distribution. When they say difference, right, that's a $500 word for minus. You take the biggest value, you subtract it from the smallest value. That's it. All right. That's your range. Let's look at an example real quick. So a large bakery regularly orders cartons of Maine blueberries. The average weight of the cartons is supposed to be 22 ounces. Random samples of cartons from two suppliers were weighed, right? Supplier one, supplier two. The weight in ounces of those carts were as follows, right? I want to know what's the range for each supplier, all right? So what am I asking you to do, right? Take the biggest number in supplier one, for example, subtract it from the smallest number. What's that? What's that number that you get? 10, okay. And then in supplier two, I want you to do the same thing. Take the biggest number and then subtract it from the smallest number. And what do you get? 10, all right? So those are your ranges. So compute the range of carton weights from each supplier. Range is equal to the largest value minus the smallest value. Supplier one, 27 minus 17 is 10. Supplier two, 27 minus 17 is 10. Yay. We found that. All right. So part B says to compute the mean weight of cartons from each supplier. In both cases, the mean is 22 ounces. So when I add up all those numbers for supplier one and for supplier two and divide by the numbers that are there, which I think is five, right? You're going to get a mean of 22 for both. So how do I tell which supplier is superior to the other? That's what I'm trying to get to. Because they have the same range, they have the same mean, right? The same average. So look at the two samples again. The samples have the same range. Look at that real quick, right? There you go. The samples have the same range and mean. How do they differ? The bakery uses one carton of blueberries in each blueberry muffin recipe. It is important that the cartons be of consistent weights so that the muffins turn out right? So looking at supplier one and supplier two, which one looks more consistent? Supplier one, okay. All right. So all right, it is important that the cartons be consistent weights so that the muffins turn out right. Supplier one provides more cartons that have weights closer to the mean, or put another way, the weights of the cartons from supplier one are more clustered around the mean. So the bakery might find supplier one to be more satisfactory than the other one. All right. This makes sense?
Yes.
Okay. We don't want no muffins with like less than adequate blueberries in it. So as we see in example five, right? Although the range tells us the difference between the largest and the smallest values in a distribution, it does not tell us how much other values vary from one another to or from one another or from the mean, right? So what I'm kind of hinting and getting at, right? We want to talk about variance and standard deviation. This will be asked on your test. Okay. So we need a measure of the distribution or spread of the data around an expected value, either X bar or mu. Variance and standard deviation provide such measures. Formulas and rational for those for these measures are described in the next procedure display. Then examples and guided exercises show how to compute and interpret these measures. So as we will see later, the formulas for variance and standard deviation differ slightly depending on whether we're using a sample or the entire population. Okay. So we're gonna a little procedure. All right, so this is how to compute the sample variance and sample standard deviation, right? So we have quantity X, for example, description. The variable X represents the data value or the outcome, right? For our mean, we have X bar. Remember, X bar is the sum of X divided by N, right? So this is the average of the data values or what you expect to happen the next time you conduct the statistical experiment. Note that N is the sample size. Next, we have X minus X bar, and this is the difference, right, between what happened and what you expected to happen. So This represents a deviation away from what you expect, all right? And is a measure of risk, right? The sum of x minus x bar squared, the expression sum of x minus x bar squared is called the sum of squares, all right? So the x minus x bar quantity is squared to make it non-negative. The sum is over all the data, right? So if you don't square x minus x bar, then the sum of x minus x bar is equal to zero because the negative values cancel the positive values, right? So this occurs even if some x minus x bar value are large, indicating a large deviation or risk, right, in the data. Last but not least, all right, so the sum of squares, right? If we have the sum of x minus x bar squared, this is an algebraic simplification of the sum of squares that is easier to compute. The defining formula for the sum of squares is the upper one, right? And the bottom one, this is the computation formula. The sum of x squared minus the sum of x squared divided by n, and that's the computation formula for the sum of squares, all right, is the lower one. Both formulas give the same result. Blah, blah, blah. Chapter 3, formula sheet. If you look at where it says sample standard deviation, and you look at where it says computational formula, what it's trying to say is that these two formulas will give you the same answer. So when you're on your test, you do whichever one is easiest for you to understand. You can use either or, right? My favorite is the bottom one, the one that's the computation formula. I think that's the easier one to use if you wanted me to pick one for you. Mhm. And that would be the same bottom formula that's here on the board as well. All right. All right, let's take it up a notch. Let's talk sample variance. All right, so the sample variance is S squared. The variance can be thought of as a kind of average of the x minus x bar squared values. However, for technical reasons, we divide the sum by the quantity n minus 1 rather than n. This gives us the best mathematical estimate for the sample variance. The defining formula for the variance is the upper one. The computation formula for the variance is the lower one. Both formulas give you the same result. So here they are on the board, right? With the variance for the top one, the variance for the bottom one. I like the bottom formula for you guys. The top one is more complicated. For the bottom one, all you need to do is just add up all the x's in a column and then square each individual numbers and then add those up to get the sum of x squared. Then you just plug it in and boom, 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 and then that's it. That's the variance, right? Just my opinion. All right, you guys can do whichever one you feel comfortable with. All right. Let's say we have a sample standard deviation right? So our sample standard deviation is the square root of the variance or the square root of the sum of x minus x bar squared divided by n minus 1, or the square root of the sum of x squared minus the sum of x squared divided by n and then divided by n minus 1. All right? So this is the sample standard deviation S. Why do we take the square root? Well, if the original x units were, say, days or dollars, right, then the s squared units, right, would be days. Sorry, then the s squared units would be days squared or dollars squared. Wow, that's true. We take the square root to return to the original units of the data management. The standard deviation can be thought of as a measure of variability or risk. Larger values of the sample standard deviation implies greater variability in the data, right? The defining formula for the standard deviation is the upper one. The computation formula for the standard deviation is the lower one. Both formulas will give you the same result. Questions on this? All make sense? Okay. Question? Are you good? Good. In statistics, the sample standard deviation and sample variance are used to describe the spread of the data about the mean X bar. Then the next example shows how to find these quantities by using a defining formula, right? And then exercise 3 shows us how to use the computation formula. So as you will discover, for hand calculations, the computation formula for S squared and S, right, for variance and standard deviation are much easier to use. However, the defining formula for S squared and S, right, emphasizes the fact that the variance and standard deviation are based on the difference between each data value and the sum. Okay? For the defining formulas for sample statistic, the sample variance S squared is equal to the sum of x minus x bar squared divided by n minus 1, and the sample standard deviation S is equal to the square roots of the sum of x minus x bar squared divided by n minus 1, where x is a member of the data set. X bar, right, is the mean, right? X bar is the mean, and n is the number of data values. So the sum is taken over all data values. Questions? Okay. Computation formulas, right? Sample statistics. So sample variance S squared is equal to the sum of x squared minus the sum of x squared divided by n, and then all of that divided by n minus 1. The sample standard deviation is you take the variance and just square root it, and then that's it. where X is the a member of the data set, X bar is the mean, and N is the number of data values, right? And then the sum is taken over all data values. And that's it. Let's look at an example. Even though this says defining formula, you could use whatever you like to do. So Big Blossom Greenhouse was commissioned to develop an extra large rose for the Rose Bowl parade. A random sample of blossoms from hybrid A bushes yielded the following diameters in inches for mature park looms. Boom. Use the defining formula to find the sample variance and sample standard deviation. Go ahead, you guys try. I want the standard deviation. Yeah, please use the formula sheets also if you need to. You guys will have it on the final, so I want you guys to be used to it. So, well, you said it doesn't matter what's wrong with you, you still want it to see. I'll say, yeah. This is what you think is easier. Yeah, I'm biased, so I like this one right here. A big one that y'all got. Seven. Looks good. He squared it. Hmm. It's all right. We count it, so. That's the eight. I really just see that sort of. I think it would go on the test, so but you can't do this stuff. It's why we live in the lines to the square. Well, yeah, you don't serve, you don't get points, so because they want the actual number of the time. All right. Stretch my feet for a little bit. So I'm gonna go through it my favorite way, and then I'm gonna show you your other option that y'all could have done it. Mhm. I'm gonna cheat a little bit because I'm not that good at math as y'all are. I'm just trying here. So first thing we want to do, we want to write down all our numbers there, right? So we got 2, 3, 3, 8, 10, 10. All right. Just to make that a little bit bigger so you can see what I'm doing. What I did, just wrote down all the numbers. So 2, 3, 3, 8, 10, 10. By the way, if you did this Horizontally, that's okay too. No problem. All right. And then now on this next side, I want to square all these numbers. So for example, right? If I have like 2 squared, we know that that's what? That's 4, right? 3 squared, we know is what? Is 9, etc. All right. So 9, 64, 100, 100, right? There we go. After that, what I want to do, I want to add up all these numbers here. And then I also want to add up all of the square numbers over here. All right. Now, here's where I'm going to cheat a little bit. Just going to square all these numbers. And then here goes our sums real quick. So all I'm doing, I'm just adding up all the numbers. All right, nothing special here. Okay. So I just wanted to get those answers right there, right? So we have 36 and we have 286. All right. After that, go straight into your variance formula. All right. Not making this up, just copying from the formula sheet. So s squared is equal to the sum of x squared minus the sum of x squared divided by n, and then all of that divided by n minus 1. After that, just plug in your numbers. Nice and simple, right? So the sum of x squared, that's 286 minus 36 squared divided by n. And hold on, I don't remember how many numbers I have. It's 6 numbers. Appreciate you. Thank you so much. All right. Divided by 6, and then all of that divided by the 6 minus 1. Then after that, little calculator. Then that's it. I'm going to cheat because, again, I don't know what that is. So this is what, 286 minus, let me see, 36. What happened? Oh, 36 squared. Yeah, it's going to do it for me. It's all good. Divided by 6. And then all of that divided by 6 minus 1. Boom. So when you do all of this in the calculator, you come out with what? 14. Right? And then to find the standard deviation, which is what we've been asked to find, right? What you have to do is you have to square root your variance. In this case, we're going to square root the 14. And that's our standard deviation. Let's actually do that and get the answer out. Square root of 14. Let's see what that is. So in my calculator, I got 3.741657. Now, me personally, I don't like to round, but if you guys want to round it off at some points, you can, but you got to round correctly. Um, I like 4 decimal places. I like 4 numbers after the decimal. That makes me happy if you want to round it off. But to be honest with you, I'm not really a fan of rounding. I just kind of write everything, whatever the calculator gives me. Questions on this? Make sense? All right, let's look at the other way. 'Cause I did say that there's 2 ways and they're going to give you the same answer, right? So if we're using the other way to do it, the first thing we got to do is we got to find the mean. All right. So several steps are involved in computing the variance of standard deviation. A table will be helpful, right? So since n is equal to 6, we take the sum of the entries in the first column of the table and divide by 6. So the sum of x we knew was 36 divided by 6 is just 6. All right. And then we make a table, just like similar to what we made, but now instead of 2 columns, we need 3 columns. All right. And then in column 1, you have the original x's that you were given. All right, at the start of the problem. Column 2, we're just finding the difference of each x value from the mean, right? So 2 minus the mean, which is 6, which is going to give me -4. 3 minus 6, -3, etc., right? I'm subtracting each x value from the mean, right? Then I want to square all of those subtractions. So -4 squared, 16, -3 squared, 9, -3 squared, 9, 2 squared, 4, etc. Then I want to add all of those squares, right? So 16 plus 9 plus 9 plus 4 plus 16 plus 16, it's going to be 70, right? Once I have that number, I can go straight to the formula. So using this value for x bar, we obtain from column 2 the square of each value in the second column to obtain column 3, and then add the values of column 3 to get the sample variance, which is divided by the sum of column 3 by n minus 1. So since n is equal to 6, n minus 1 is equal to 5. So the sum of x minus x bar squared is going to be equal to 70 divided by 5, which comes out to our 14. And then now to obtain the sample standard deviation by taking the square root of the variance. So we square root the 14 and we come back out with the same answer, 3.74. So me personally, I like that bigger formula because I only have to make a 2-column chart to get it. In this process, you need 3 columns to get the final answer. So that's my preference, all right? No pressure in whichever method you want to use. You could use whichever one you like. I like this method. I like my method more because it's easier and quicker. Mhm. Questions on this? Good. All right, let's talk about it just a little bit real quick before we move on. So, what does measures of variation tell us, right? Measures of variation gives information about the spread of the data. The range tells us the difference between the highest value and the lowest value. It tells us about the spread of the data, but does not tell us if most of the data are or are not closer to the mean. So it's telling us, the range is telling us how far out the data in general is spread, but it's not telling us individually how far all the numbers from the mean individually. That's what our standard deviation is telling us. All right. So the sample standard deviation is based on the difference between each data value and the mean of the data set. The magnitude of each data value enters into the calculation. The formula tells us to compute the difference between each data value and the mean, square each difference, add up to the squares, and then divide by n minus 1. And then take the square root of the result. The standard deviation gives an average of data spread about around the mean. The larger the standard deviation, the more spread out the data are around the mean. The smaller the standard deviation indicates that the data tend to be closer to the mean. The variance tells us the square of the standard deviation. As such, it is also a measure of data spread around the mean. Okay. Just want you guys to understand a little bit. We'll just talk a little bit more about the Greek letters, because they're going to keep coming up. Not on your test, but for your own knowledge. So in most applications of statistics, we work with a random sample of data rather than the entire population of all possible data values. However, if we have data for the entire population, we can compute the population mean mu, the population variance sigma squared, and the population standard deviation sigma, which is a lowercase Greek letter, using the following formulas. So now we're going to talk about those formulas on the formula sheet. All right. So population parameters, right? Okay. Yeah. You want it? Oh, okay. I got you. All right. So population mean, right? Mu is equal to the sum of x divided by um capital N, which is again our entire population size. Population variance sigma squared is equal to the sum of x minus mu squared divided by the capital N, which is our population size again. Population standard deviation sigma is equal to the square root of the sum of x minus mu squared divided by capital N. Again, you don't have to use this formula if you don't want to. You can use the other one, get the same answer. All right. I like the other formula more. So where n is the number of data values in the population and x represents the individual data values of that population. All right. Let's make a couple more comments real quick. So we know that the formula for mu is the same as the formula for x bar, the sample mean, and that the formulas for sigma squared and sigma are the same as those for the sample standard deviation and the sample variance, right? S squared and S, right? Sample variance, sample standard deviation, except that the population size capital N is used instead of N minus one. Also for mu, right, is used instead of X bar in the formula for sigma squared and sigma, right? Sigma squared is our population variance. Sigma is our population standard deviation. Just for your knowledge, not being asked on your test. All right. So in the formulas for sample standard deviation and population standard deviation, we use n minus one to compute the sample variant, excuse me, the sample standard deviation, and capital N to compute the population standard deviation. Why? The reason is that N, capital letter, represents the population size, whereas N, lowercase letter, represents the sample size. Since a random sample usually will not contain extreme values, large or small, we divide by N minus one in the formula for the sample size. Excuse me, for the sample standard deviation. That's what I meant to say. All right. To make the sample standard deviation a little larger than it would have had we divide by n, right? So courses in advanced theoretical statistics, yay, show that this procedure will give us the best possible estimate for this standard deviation sigma. In fact, the S, right, the sample standard deviation is called the unbiased estimate, right, for the population standard deviation. So if we have the population of all data values, then extreme data values are, of course, present. So we divide by capital N instead of N minus one, capital N minus one. All right. So now we kind of talking a little bit about inferences, right? We're gonna get deeper into that later on. Not today, but just to get the vocabulary out there. All right. And then in case you're wondering, for my favorite formula, here it is for the population standard deviation. This one is not on the formula sheet, but you guys can basically know about it. The computation formula for the population standard deviation is sigma is equal to the square root of the sum of x squared minus the sum of x squared divided by capital N and then divided by capital N again, right? And we've seen that the standard deviation sample or population is a measure of the data spread, all right? And that's it. Questions on standard deviation and the process of how we go about to do it. Is everything's clear? All right. So we literally just went through question one on your final. You're gonna be given a data set, right? With some numbers. I don't know what the numbers are. All right. They're gonna ask you what is the mean? What is the median? What is the standard deviation? And that's what you're gonna give me back. And that's it. No. No. That's more of I want you to understand where the defining formula is coming from, you know? But probably in like your actual like major classes, they'll ask you for something like that. Especially when you go for like nurse practitioner and stuff. All right. Again, no homework today, but I'll make up for it tomorrow. And it's okay if you're a little bit behind with the homework because you'll have the weekend to make it up. You know, you have plenty of time. By the way, I know I mentioned tutoring earlier. I didn't mention this though. Tutoring is both in person and online. So if you guys have to go after class or say you want to get something to eat or whatever, and you want to go home and then do tutoring, you could do that as well, right? Till 6. So that's another option for you guys as well. Okay. I'm sorry?
So it's
Every day. Yeah. Both in person and online. So whatever works best for you. All right. I hope I can finish this topic. So I want to jump into another question called scatter diagrams and linear correlation. This is on your final as well, doing a scatter diagram. I'm not going to ask you to give me the correlation coefficient, the R, but I am going to ask you to actually do the scatter diagram. So, right? So let's talk about it. So studies of correlation and regression of two variables usually begin with a graph of paired data values x and y. We call such a graph a scatter diagram, right? Scatter diagram. Give you all a little definition. So a scatter diagram is a graph in which the data pairs x and y are plotted as individual points on a grid with horizontal axis x and vertical axis y. We call the explanatory variable as y is the response variable. All right. Again, a little bit technical there, but long story short, whatever value you plug in for x, get a y value out. That's all y'all need to know. All right. And then by looking at the relationship between X and Y, right? You can see if it's a linear correlation or not. All right. Real quick, I just want to just like jump into an example. Hopefully we could elaborate on it a little bit and time doesn't run out against us. So phosphorus is a chemical used in many households and industrial cleaning compounds. Unfortunately, phosphorus tends to find its way into surface water, where it can kill fish, plants, and other wetland creatures, right? Phosphorus reduction programs are required by law and are monitored by the Environmental Protection Agency, EPA. All right. I wonder what's going to happen to the EPA when we change leadership. Anyway, here we go. A random sample of 8 sites in a California wetland study gave the following information about phosphorus reduction in drainage water. In this study, X is a random variable that represents phosphorus concentrations in 100 milligrams per liter. At the inlet of a passive biotreatment facility, and Y is a random variable that represents the total phosphorus concentrations in 100 milligrams per liter, right? At an outlet of the passive biotreatment facility. Yay. So here we go. Here we go. All right. That's our data. All right. So X is our phosphorus concentrations. Y is our total phosphorus concentrations. That's simple. X individual, Y total. One is at an outlet, one is at an inlet. So what do I want you guys to do with this information? I want you to make a scatter diagram, right? Which is like an XY plot, more or less. Let's look at how to do that together. All right. So you guys remember the Cartesian plane, right? When you have like this is the x-axis, this is the y-axis. We're on the same page, right? All right. This is just a tad bit more simple than this what you call it quadrant thing that we have here, right? I'm only interested in this one right here, the first quadrant. That's all I'm really interested in, the first quadrant. All right. Um, I'm gonna erase this because I need space. But I'm just drawing the first quadrant. That's all I really care about. There you go. And again, this is why my y-axis, this is my x-axis. All right. So my y-axis, this is for my outlet. This is the outlet. That's supposed to be an O. And then X is the inlet. This is just from the story. Every story will have a different name, right? This is where you put the names, right, of the data that you have. The X is the horizontal axis, so that's the name of it, right? The Y is the vertical axis, and that's the name of it, right? In the story that we had with the phosphorus, that's the outlet and the inlet, all right? Long story short, I want to graph these, right? Now you can graph them using dots or whatever you want. Me personally, I'm an X fan, so I like to put X's where my dots would go. All right. But before we could do that, right, I have to figure out a kind of range, right, for my X-axis and my Y-axis. So I'm looking at my X values here. Let's see, 5.2, 7.3. What I'm trying to figure out is what is the biggest number there? My biggest number there is 8.3, right? 8.3. So that means that I know that I have to get to 8.3, maybe a little bit bigger than 8.3, but I have to get to something like 8.3. So how do I want my numbers on my axis to increase on the bottom, right? On the horizontal, right? I feel like I'm going to do them by ones. I feel like ones is good enough, right? So 1, 2, 3, 4, 5, 6, 7, 8. I need a little bit more. 9, and then that's good enough, right? This is completely up to you. If you wanted to go by twos, that's fine. You want to go by fives, it's up to you. Depends on the story, depends on what you want to do, right? No pressure. I just looked at the numbers and I thought that ones made more sense for me, right? I'm going to do the same thing with the Y's now, right? So I'm going through it. I have 3.3, 5.9. I'm looking for what is the biggest number I could find there. And it looks like 7.1 is the biggest number. So I know that I have to get to 7, right? Maybe even above 7, right? And I can do this however I want, right? So, you know what? Just to prove it to you, I'm going to do it by twos, right? So 2, 4, 6, and 8. Just to prove to you that I can go ahead. Oh, yeah, go ahead, go ahead. No problem, no problem, right? So, what I'm going to do now, right? Each one of these numbers together, each one of these numbers together, they're a pair, right? Think of it like a marriage, right? X and Y, they go together, they're a pair, right? I'm looking for where they intersect at, right? So, for example, the first pair is 5.2 and 3.3, right? So, what am I going to do? On the X axis, I'm going to come across to where I believe 5.2 is. I think 5.2 is somewhere like here. I'm just making it up. And the X is 3.3. So I feel like it's somewhere like here. It's not exact, but you get the idea, right? Like my first value is going to be here, right? So you come across the X, go up to the Y, and then that's where you get the first value. And then you go on and do the next one and the next one and the next one until we have our scatter diagram. All right. Let's do it. Next one is 7.3 and 5.9. So I'm going to go on the x-axis. I'm going across to where 7.3 is. And I'm going up to 5.9. I believe 5.9 is going to be somewhere like here. And again, we're not computers. I don't expect you to have like the perfect graph. Just give me the best that you can. All right, you're just doing the best that you can. That's all that is. All right. 6.7 and 4.8. So I'm going to go 6.7 and then 4.8. I believe that that's somewhere like here. And I have 5.9, 4.5, 5.9, 4.5, I believe is like here. 6.1, 4.0, 6.1, 4.0. I feel like that's like here. And then I have 8.3, 7.1, 8.3, 7.1. I feel like is like here. And then I have 5.5 and 3.6. So 5.5, 3.6. I feel like that's like right here. And then I have 7.0 and 6.1. So 7.0, 6.1. I feel like that's like right here. Okay. That's all I'm looking for. Questions on this? That's good. All right. The next question that they're going to ask you when you do this graph, right, is what do you think? I'm going to say this now. What would you estimate, right, the correlation coefficient to be, right? Like the least square line. Would you think that this graph is positive or negative. They're also going to ask you about zero. And I'm telling you this right now. There is no such thing, right, as a zero sloped graph, right? In scatter diagrams. No such thing. That is a theoretical example in the textbook that will never happen, right? Your numbers will always be slightly more positive or slightly more negative than one thing. It could be close to zero, but it will never be true zero. So now you tell me, looking at this, do you think that these points on this graph are they increasing or are they decreasing? Are they positive or negative? What would you say? Positive, right? They're positive. I like that, right? And we're gonna say positive because what's a good color? What's a good color? Let's go with the purple, right? We're saying positive because if I was to draw a least square line through this data, like so, right? And how do we read these lines? We read this from left to right, the same way that we read a book. This line is increasing. So part A is to do that graph. Part B is to say if it's positive or negative, and we said positive. Part C is going to ask us to interpret this graph, interpret it, right? And here's the interpretation. If it's positive, right? If it's positive as X, which in our case is the outlet, is increasing, Y, which in our case is the inlet, is increasing. Right? That's it. That's your interpretation. If the graph was negative, your interpretation would be as X is increasing, Y is decreasing. Okay? Let me say it one more time. If the graph was negative, the interpretation would be as X is increasing, Y is decreasing. All right? In a nutshell, that's the scatter diagram. In a nutshell. Right? There is more to talk about, but I am concerned about time. Go ahead. Yes. Sure. No problem. Up top here, you want the story also? Just okay. There you go. You're welcome. Just to show you guys what the computer outlook for this would be, this is it for phosphorus reduction. All right. Again, we're just doing the best we can. This is a computer doing the actual point where it's supposed to be and all of that. All right. But we agree this is a positive correlation, right? And as the X is increasing, the Y is also increasing from left to right, the same way that we read a book. All right. I just want to show you guys real quick. We have a scatter diagram like so. Right. This is positive correlation. This is negative correlation. All right, just so that you guys can say that you've seen it. Is there any questions on this? Any at all? So if I'm doing the graph, I want you to label your axes, label the x-axis, label the y-axis with whatever the story is that they gave you. Make the dots, or if you like X's like me, do X's, whatever. It doesn't matter, right? And then tell me, is it a positive correlation or is it a negative correlation? The correlation will not be zero. It's either positive or negative, right? You're just going to tell me what you think it is. And then after that, you're going to interpret it, all right? For the interpretation, as X is increasing, if it's positive, Y is also increasing. If it's negative, then Y is decreasing. That's it. Any other questions on this? Feel good? All right, that's pretty much all I have for today. Let me just talk about the scatter diagram real quick, what it's telling us. And then we could tap out at that. So what does a scatter diagram tell us, right? A scatter diagram shows the relationship between two paired variables, x and y. For each pair, x comma y, of a data set, we plot the point on a grid with horizontal axis x and vertical axis y. To the extent that the data points on the graph fall closer to a straight line, we say that the relationship between x and y is more linear, right? To the extent that the data pairs are scattered over the graph, we say that there's no linear relationship between x and y is apparent, right? So I'm telling you right now, on your test, you will not have this zero correlation thing, all right? That is only a theoretical example in the book. It's not going to be on your exam. It's going to be either positive or negative. You just got to do the graph and then tell me what it is, and then interpret it. As X is increasing, what is Y doing? Is Y increasing, also making it positive, or is Y decreasing and making it negative? That's it. So again, I'm gonna work on homework for you guys for tomorrow. Yeah. So I am recording today, so you guys can always go back and watch this back if you like. Trying to see if there's anything else to talk about. I feel like we're good for today. Probably when we come back, we'll talk about probability in general. Little compound probability. We'll talk about the and the or, the table. Remember that? Yeah, we're gonna do that too. Not on your test, but we're gonna go over it though. But we're gonna go over it though because it's fun. Yeah. Tutoring is open right now if you guys want to go there and practice some more. All right. So all we did was we did mean, median, standard deviation, and we did scatter diagrams. All right. So you guys are welcome to go there. Um, If you want to go home and do it, you can too, because there's tutoring online as well. No pressure. So let's talk about that. So to get to tutoring online, bop, bop, bop. Let me stop sharing. I'm gonna share back. Hold on 1 second. I'm gonna show you guys online. This is a good question. All right, 1 second. Okay, so you're on Google, right? You want to type in BCC and WC online. WC online, right? So then you want to click on this website. Now, if it's your first time, right, you're gonna click right here where it says register for an account. It's not that bad. You guys can go do it right now if you want in there, right? You just kind of fill this out, all right? Just fill this out, and then after you fill it out, you're gonna have an account, right? When you go into login, let me go back to the home real quick. When you go into login, you're gonna see the different kinds of tutorings that are available at BCC, right? Now, if you want to do online, like what you just mentioned, right? You click where it says Math Tutorial Lab, Winter 25 online, right? And then you log in, of course, and then you're gonna see a schedule come up. You just pick the time that works for you, and you book the tutor, and then that's it. What's gonna happen is they're gonna send you an email to confirm your appointment. Inside of that email is gonna have a Zoom link in there, and the Zoom link will take you to the online tutoring suite, right? Also, you can also in reverse do this in person as well. This is the link for in person. Just log in or whatever. You can book one-on-one time. Say if you wanted to work with me or you want to work with another tutor in person, you can just make an appointment here if you want that special time. But you guys are also welcome to walk in to tutoring and get help as well, you know. But if you want to like, get that personalized time, be my guest. All right. You're welcome. Thank y'all for coming. You're welcome. I'll see you tomorrow. Yes. Have a good night. And then I'm gonna upload this to Brightspace, so just watch your emails and stuff.